Hello everyone and welcome back to this next lecture in the machine simulation series, and this is where we had left off last week, where we had did a little recap of the single phase equivalent induction, or rather the equivalent circuit of the single phase induction motor, and we had gone through all the different parts of the equivalent circuit, as well as we had discussed the different ways in which we can estimate or calculate the parameters of this equivalent circuit. Now in this video, I'm going to start by building the simulation and slowly starting to program it as well. So, as always, before I start the video, a little bit of brief background that if you're interested in these kind of video lectures, but you would like something a little more comprehensive, I have full-length online courses which you can find on my website, which is pythonpowerelectronics.com. So on this website, you can just go to the button Learn, and this will take you to the page where all the courses are listed. So these are the courses which I have currently. So the very first course I have is Simulating Power Electronic Circuits using Python. And in this I talk about the very basics of how you can use Python and Python Power Electronics to simulate basic power electronic circuits. The second course is Basics of Digital Signal Processing for Power Engineers. And in this I talk about how you can use Python and the Python packages like SciPy and Signal to design and analyze filters for power engineering applications. The third course I have is Simulation of Magnetics for Power Electronics using Python, and in this I talk about how you can simulate magnetic components like inductors, coupled inductors and transformers using Python and Python Power Electronics. The fourth course I have is Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python and packages like the Python control package to design and analyze controllers for power electronic applications. And I take the example of a single phase grid connected converter to design and analyze controllers. And the very last course I have is a free course called Why Specialize in Power Electronics, and this is more of a motivational course targeted toward high school students or junior undergraduate students who are yet to choose their domain of specialization, and to talk about some of the advantages or rather challenges and opportunities available in power electronics. So all these courses are hosted both on Udemy as well as Decibel Labs. So check out whichever you want depending on your geographic location or whether there are any promotions available. So with this, let me get back to my lecture. So this is where we were. So we are trying to simulate an induction motor connected to a single phase supply. So basically, everything to the right of this is the induction motor. So if we consider these are the terminals, we will see that everything to the right of this can be considered the induction motor, which is connected between two terminals. And these terminals are connected to the single phase supply. So what we would do is we need to convert this entire model into an control file. So this will have to be modeled in a control file. Now, unlike a transformer, there is one level of complication, and that is that this is a rotational machine. So which means along with the electrical part and the magnetic circuit, there will also be a mechanical component, and that mechanical component will define the slip S. Correct? Because as I said, the slip S is defined as the synchronous speed minus the rotor speed divided by the synchronous speed. So we do need to have the rotor speed for this purpose, for calculating the slip. So the way we are going to go about it is, as always, we are going to connect this single phase supply to an induction motor which will be modeled as a voltage source in series with a resistance, and thereby forming some form of a current source. Because what we're going to do, we're going to take this voltage source, apply it to the induction motor, and according to the voltage source and the state of the machine, which means depending on the speed, this motor will draw a certain current. And this current which we compute will be adjusted by the voltage source in series with the resistance. And this is something we've done way before we started this, of how we design a controllable current source. So let me go and start with building a simulation. So this is my simulation library, and this is where I had done the load as a current source. Right? So in this load as a current source, let me go over to my file browser and let me go to simulations. This is where I was. We had taken this current source. Let me check out. This is we will use these files or rather similar files in our new circuit, and we are going to then, instead of having simply a current source, we are now going to have it as an induction motor, right? So this is our controllable current source, and controllable current source consists of a voltage source in series with a variable resistance, and we're going to measure the voltage across the terminals. So depending on the voltage across the terminals, we can adjust this voltage source to produce a certain current. This is covered already in the beginning of this video lecture series. So check out those videos if you're not sure about what I'm talking about. So in the meantime, let me just check this out. So this is the circuit that we can continue to use. We have the voltage source, this is a parasitic resistance, and this is connected across an RL load, right? This is connected across an RL load, and we're going to measure the voltage across it. So we can use this as well, right? So let me go and start a new simulation, and let me call this single phase induction motor, and let me call this one coil, or rather only main coil. And the reason why I'm saying this is, as I said, an induction motor will have a main winding and will have an auxiliary winding. The reason is, if a single phase induction motor has only a main winding, it will not be self-starting. This auxiliary winding is necessary to make a single phase induction motor self-starting. But for now, we will start with just the main winding, and we'll find out why a single phase induction motor with just a main winding is not self-starting. So I'm going to call this only main winding. And for now, let me just copy it here. And we are not going to have any power electronics, so therefore 1 microsecond is good enough, 1 second time duration is good enough, and the rest is okay. All we have to do is choose the directory. So let me go back to my file browser, and I can choose this because this is where I had this equivalent circuit. Actually, maybe I will choose another one, because let that be as it is. Let me say basic, or rather single phase induction motor, and let me call this main winding, right? So that I'm fairly explicit. Now here, let me go over and copy this file, because this is the file that we would like to start with. Take the properties, choose the parent folder, go back to the file browser, paste it here, right? And save it. So if this page comes, it means it has accepted the directory. And if you go, you will find now a test file. So we're good to go. So let me go over and make sure I close it. And let me go and pick out, along with this, the params file. Okay, so that we can import the parameters right away. So let me rename this, and let me call this single phase supply and .csv. So I will just pick out the rename, copy it, and just paste this suffix, or rather prefix, not suffix, prefix before the params file so that they are compatible, right? So again, let me now open this, and this is my single phase supply. So only a few changes we should make, and that is something which we have already done, is we have taken into account some parasitic resistance of the voltage source, and there is also a parasitic resistance of this branch, right? Along with this, we should also copy over the current source file. So let me go over here and let me copy these two files, right? So because for now, in this current source, all we are looking at is generating some arbitrary current, right? That's all we are looking to do. And let me go back here to my browser and let's go and start. So let's go to the add circuit file, choose the correct directory, choose single phase supply, call this supply, save, choose the file, current load. Actually, instead of current load, let me go and rename this. Actually, maybe I can just leave it as it is, does not have to change. Current load. And let me call this as current source. And I can save it. I can process the circuit schematics. It should work because it worked before. There are no detectable errors, so we're good to go. Let's pick out edit circuit parameters. Click on current source load. All we have to do is import the parameters. So let's just quickly go through the parameters. Current source 1 amp meter is this one, and it is pointing in the downward direction, which is perfectly okay because it is a load. Current source voltage load is pointing upwards, which is also okay because it is a load. It has to generate a current so that it draws, or rather generates a voltage according to the terminal voltage such that it draws a current, which is also okay. Variable resistor is 100 ohm for now, which is okay, we can change it later. And the voltmeter is measuring 1000 volt because we are assuming a 240 volt supply. All okay. And let's go over and pick out single phase supply params and upload it. So let's have a look. Ammeter VN 1B 1C. This is the single phase supply. This is this ammeter which is measuring, and it is measuring current towards the right, which is perfectly okay because it's a source. Then there is ammeter load, which is measuring downwards, also okay because after all it's a load. The resistor of this voltage source is a parasitic resistor of 10 milliohm, that is also okay. And the same goes for the resistor feeder 1 because this is a parasitic resistance of that branch. That's just 10 milliohms. The voltage source is a single phase supply. Now, since I'm in Germany, I am using 339 volts, which corresponds to a 240 volt RMS AC supply. And the frequency is 50 Hz. If you're in North America, you can change this to 60 and make this around, I think, 160, because it will be 120 volt RMS, which corresponds to around 167 or 170. You just have to calculate 120 multiplied by root. So wherever you are, change it according to the single phase supply that you are actually getting at your location. And finally, the voltmeter of the load, which is also 1000 volts, and all this is okay. So since now we have this, we can now continue to now do something else, and that is we now have to create the control file. Now there are two control files, right? For now I'm going to start with just the same old single phase supply. That is, we're going to take this current load and we're going to pick out this load variation.py. Right? So let's go over to the editor and check out what this is. Let me collapse this thing. And let's look out load variation.py. Let me close this. So here, as you can see, this model is for a variable load, right? Is for a variable load. And here I am only calculating finally what should be the voltage that appears for a particular current, right? So basically I have calculated a particular resistance that I would like to, or rather load which I would like to emulate, and this load is an RL load. So it's 100 ohms and 0.3. So it's almost, you could say they are almost equal, right? So now that we have this, what do? We are now calculating this, the current drawn by this load with respect to this simple KVL equation, right? And it's a very simple KVL equation because it's a simple RL load. Now what we are going to do is we can use it, but now instead of calculating the reference here, we will calculate the reference in another control file which will contain our induction motor simulation model. That induction motor simulation model will produce the current which is going to be used here, right? So we are going to remove this. For now I'll keep it as it is, but we will eventually remove it. So let me just put a little comment here saying to be replaced by induction motor model. This is what we're going to replace it with, right? Now the load variation is also not a very good file name, so I'm going to rename this to let me call this load model, because it's a load model, and we are going to model in this case an induction motor as a model. Load model descriptor. So this is what we have. So all we have to do is go over, choose this file, and just say load emulation, because we're just trying to emulate a particular load. It can be anything. It can be any load which is drawing a certain current which is being calculated in some manner. For now it's a simple RL load, but it can be calculated replaced by an induction motor or any motor. So all we have to do, configure the file. We just have to add the descriptor and upload it. So let's quickly go through it. We are measuring the terminal voltage. As I said, that's important. The output is the voltage source and the resistance, right? And the static variables are the current reference, the voltage source, which we are going to be generating, and the time event variable is extremely important in any control file. And finally, there is a variable storage elements, which we are measuring only for the purpose of our own debugging. We can delete this later. So let's come over here and pick this out. So as I said before, we will be removing all these, right? And we'll be removing this and replacing it by a global variable. So this is what we're going to do. So just for now, let's just come and run this simulation, make sure it at least works. And always go to the command line and make sure there is no error, right? If there is an error in the Python code, it will not show up in the browser, but it will show up in the command line. So always, whenever you run a simulation, come over to the command line, make sure there is no error message. So this means it is okay. Let's just once have a look. Let's call this current. Actually, current plot is okay. Start it. And yeah, ammeter VN is okay, because this is the current that is being drawn by from the source. Click on done. Click on plot. It should be exactly the same as before, nothing new. And this is our current plot. So this is where we are. So far so good. We have migrated our simulation. Now, before I continue, let me at least tell you what I'm going to do next, right? Because this lecture has already gotten pretty long, so I don't want to take it further long. But let me create another file, and I'm going to call this induction motor model.py, right? This induction motor model.py is what we are going to add to our control file. It contains nothing, and that's okay, right? We're going to add this gradually. Induction motor model, and if you want, you can even be single phase induction motor model, right? Because a three-phase induction motor model will contain things like DQ transformation and several other things. So we have this. Now, what are we going to do here? Let me write a few comments and leave this and end this lecture. Here comes the single phase induction motor model. And specifically, we are going to bring in all these parameters. each and every one of these parameters. You're going to bring in the stator resistance, the stator leakage inductance, the core loss resistance, well, the core loss resistance also, but the magnetizing inductance, the rotor inductance, and the rotor resistance. All these parameters that are there in this equivalent circuit will now have to show up here in this induction motor model. So this induction motor model will include all the parameters in the single phase equivalent circuit, right? And once we have the single phase equivalent circuit, we are going to now build a magnetic model based on this, which will also take into account the speed of the motor, and we are also going to bring in the concept of electrical torque and mechanical torque, right? So this will take as input the voltage applied across the motor terminals and will produce a signal being the current that is drawn by the motor. This current will then be fed to our load model, right? This is what's going to happen. We are going to feed this to load model.py, and this load model.py will now ensure that this current is being drawn for the single phase supply. This is how we're going to simulate an induction motor. Alright, so this is a brief idea of how we're going to go about all this. It's going to take a long time because I want to take my time and gradually build up this simulation bit by bit, right? So already this lecture has gotten pretty long, so I'm going to end this now. If you have any doubts, please do either send me an email or message me, whichever is your preference. Otherwise, I will see you next week, where we will slowly start translating all the calculations from this equivalent circuit to our Python code. And later we will start with the magnetic circuit. As always, slow and steady, and that's the best way to learn. So thank you so much for watching, and see you next time. Goodbye for now.